Thank you. Thank you for the invitation. And yeah, so what I would like to do today is to give you kind of the overview of what's going on in the area of fast graph algorithm, how expander are so useful in recent years. And so first of all, we all know expanders is just like a robustly connected graph, which is sparse and still well connected. And we also know that expanders are just so great. They are useful to like for the construction of a bunch of super strong objects, right? Like error correcting code, some sorting network, fault tolerant network, and so on. So it's just an amazing object that is useful for many applications. But now, on the other hand, right, in the area of graph algorithms, we want to design an algorithm that handle any graph. It's not just like someone give you an expander. So the question is that, okay, can we still try to exploit an expander when your graph is just arbitrary? And yeah, the answer is yes. And basically what I want to show you is like what are the tools that allow us to do that, to exploit expander in arbitrary graph and get fast algorithm. Okay. So what I want to do is basically the first two parts before the break is I will kind of first flash through the tons of application of expanders to fast graph algorithm. And then the part two, which is like a big part, I will explain the tools behind this amazing application. And then the third part, I will just kind of go into some details how to construct one tool, which is for today we'll talk about how to construct something called expander decomposition. And then I talk about some future direction that is interesting. So that's the plan. So let's start with like the first part, which is a bunch of application from expander. Okay. And in this part, you will see some like keywords that I will not explain yet. I will explain it in part two. The keyword is like expander decomposition, expander routing, expander pruning. You will say like this keyword is like they make so much impact to fast graph algorithm, but I will explain in the next part what exactly they are. And throughout the talk, right, N usually just denote the number of vertices, M denote the number of edges, and I will use O tilde here to hide polylog factor, and O hat to hide like n to the little one factor, which is bigger than polylog. So it's even like cruder. And usually I will just ignore polylog and n to the little one, like this subpolynomial factor. When we have like this, the time like this, I just call it near linear time. And when we have O hat M, I call it almost linear time. This is what fast algorithm usually, like fast algorithm people usually use. This is the terminology there. Okay, so let's make it precise for this talk, right? When I say expander, I mean the following. So the graph here is a phi expander if when you take any subset of vertices S, like this thing, right? Where like the volume S is on the smaller side, what we have is that the cut size of S compared to the volume is big. Okay. So this thing is just the cut size of S. It counts the total weight of edges crossing S. Yeah. Okay. And this cut size should be big compared to the volume. The volume of S is just the sum of the degree of every node inside S, which is really like the sum of the weight of edges incident to S. So it's an edge expander. So this cut size should be like at least 5 fraction like of the volume. And if there is some cut S such that the cut size is smaller than 5 times the volume, then I said that this cut S is a phi sparse cut. So when we said that the graph is a phi expander, I just really mean there is no phi sparse cut in the graph. That's the terminology here in the talk. Okay. And now, okay, so we know that when phi is a constant, such an expander exists. Right? However, like in this talk, expander that we're gonna talk about is like a weak one. It's a really weak one. When I said that the graph G is an expander, I mean that like G is a 1/polylog expander or 1/subpolynomial expander. It's a super weak one, but we need to work with this thing because we need to work with arbitrary graph, and we will try to find this kind of expander inside any arbitrary graph. All right, so now let me like kind of go through quickly how expander has been used in several models of computation to get fast algorithm. The first one is static model, which is just a classical model of computation. You have input, you output some output. Yeah. So the first one is basically here. The first, I think the first algorithm that really exploit expander to make the algorithm fast is the work by Spearman and Teng. So they show that if you want to compute something called electrical flow in a graph, then you can do it in nonlinear time. Previously, people know how to do it in like something like quadratic time, but they are the first, like 20 years ago, they are the first that do this in nonlinear time. And this is like one of the most influential work in the area of fast graph algorithm. After that, like it spawned a lot of like a new result, and many people like kind of follow that framework. And after that, after this work, people use it to get fast nonlinear time algorithm for approximate max flow and something called oblivious routing. Doesn't matter too much if you like about the name of the problem. The point is that each of these problems are the core problem in the area, and they use something called expanded decomposition to get the first nonlinear time algorithm. Okay. And then people get this fast algorithm for a while. Everything here is randomized, and then it turns out that several years after that, people managed to get deterministic algorithm for all above problem. And the way to get this is basically to first get deterministic version of something of expanded decomposition. And once you get the deterministic construction of this thing called expanded decomposition, then everything is deterministic. So it's like it shows that this thing is a core object in the area. And once people get that, then there are more deterministic algorithm for important problem that follows. Yeah, and this is based on deterministic expanded decomposition. So that's one thing. Also, there is another kind of fast algorithm, which is the model of dynamic algorithm. So let me tell you a bit what is this model. Yeah. Let me give you an example for this model. So imagine that you have a graph here, right? And the setting is such that you first, let's say the question is like you want to ask whether the graph is connected. Then you just say that, okay, now the answer is yes. But this is a dynamic version of the problem. So there's going to be a sequence of some update. For example, there is a sequence of edge updates, like deleting one edge here. One tree is deleted. And now you need to answer whether the graph remain connected or not. Here you just answer yes. And then next update come, you answer again. Now this is the answer is no because they are not connected anymore, right? And so on. Yes. So basically for any graph question, you can ask this kind of problem. That is, okay, you have a graph, you answer your question, but then there is a sequence of each update. Now you need to answer, like output the answer quickly after each update. The hope is not to compute things from scratch. The hope is like after just one each update, you should compute things maybe in polylog time, not linear time. That's the goal. Okay. So yeah, this is the area of dynamic graph problem where the input is a graph, then sequence of each update. And the task can be various things instead of connectivity, like I show you. It can be about maintaining some like a nice object like minimum spanning tree, or you might want to support queries. That is, you might, instead of just ask whether the whole graph is connected, you can ask given two nodes, whether these two nodes is connected or not. All kind of questions you can ask. And people do study like many questions in this area. And the goal is just to get fast update time. So the time to process each update should be polylog. That's the goal. And now it turns out that expanders are super useful in this area too. And you will see soon in part 2, like how come, what's the high level idea behind this. But the history is something like this. So 20 years ago, like static expanded decomposition was developed, right? And then like 3 years after that, people start to realize that, okay, expander is useful, but they didn't manage to use it in the dynamic setting. Like they can use it to like something almost dynamic graph. That is, they can handle just like one batch of update, not a sequence of updates. Okay. And like only 10 years after that, we managed to make it work and useful for dynamic algorithm. And the key technique that make things possible in the dynamic setting is called expander pruning, which I will define in the next part. And then after that, like tons of paper, like use expander for dynamic algorithm. Like they use it to get fastest algorithm for a bunch of important problem, minimum spanning tree and so on, and fastest deterministic algorithm on the dynamic setting. Okay. And once you get this fast dynamic deterministic algorithm, then one of the useful thing about dynamic algorithm is that you can use it for as a subroutine inside other like a big static algorithm. And one of the nice thing is that for these two applications, they are used to get like the biggest breakthrough in the last few years. That is, they use it to get the near linear time max flow. So that is a nice algorithm, and that is based on dynamic algorithm, which use expander. And everything here that I list use expander pruning. So we will at least see what is expander pruning today. And the last thing is the distributed model. So let me just tell you briefly about this model. Okay. So in this model, you have a graph, but you imagine this graph is like a large network of computer. For each node, you think of it as like a one computer that each computer can just talk to its neighbor. So like you have this graph, and the goal is that you like everyone in the network would like to basically know something about this whole graph, but everyone can just talk to only locally to the neighbor. Okay. For example, what is the mean cut of this graph? It's something like that. Yeah. So you have this graph and you have only local communication, right? So a node can send a message to only the neighbor on each route. Moreover, the number of the size of the message that you send between each other need to be like a small number, cannot be like a huge message. Think of it as one number, basically one number that takes log n bits. So that's the message that they can send to each other in each round. And the goal is to compute something about this graph and minimize the number of rounds. Let's say like, okay, what's the mean cut in this graph? At the end, everyone in the network should know how many rounds you need to talk to each other. That's the setting. Okay, and yeah, you can ask all kind of questions again. Minimum spanning tree, mean cut, shortest path, and so on. When everyone can talk to only its neighbor. Now, okay, let me introduce a closely related model. And this is called congested clique. Okay. This model is called congest. Now, there is another one called congested clique, which is like a strictly stronger model. How? That's different is that instead of having only local communication, in congested clique, you now allow all-to-all communication. So every node here actually can send a message to everyone. For example, this guy can also send a message to 4. One can send a message to 4 too. Okay. But like everyone still want to figure out like they still want to figure out some like communication, like some property about this network, right? But now we allow all-to-all communication. So it's just strictly stronger. And by the way, if you have any question, please feel free to ask. Okay, that's a 2 different model of distributed computation. And now, now you can ask, okay, what like intuitively congested clique should be like stronger, and it was the case. For example, in the problem called triangle listing, where you have a graph and you just want to list all the triangle in the graph. Okay. In congested clique model, people show how to get algorithm with n to the 1/3 round. But in congest, it is worse. Okay. And you can ask about like a listing clique or listing triangle or listing cycle and so on. Yeah. Like there is like a discrepancy between the 2 models. However, it turns out that with expanded decomposition, which I will explain, and another thing called extended routing, we managed to close the gap between the 2 models. And with anything that you can do in congested clique, there is not a black box reduction, but there is a way to get an algorithm that matches the upper bound in congested clique in congest. So what does it say? It basically says that using expanded decomposition and routing, you can transfer strong result that works in congested clique that doesn't have low quality constraint, and you can make it work in congest that have this low quality constraint. So that's the power of expander in the distributed model. So now, yeah, I hope that, okay, you kind of convinced that, okay, yeah.
Can I ask you to go back to this? So you have theta in the complex. So you have a lower bound?
There is a lower bound as well. So this is now tight.
This is actually.
Yeah. Right. So it's tight in both model. So yeah, so this is like basically kind of, I kind of show you that this expander thing really are useful in many model of computation when people care about fast algorithm. And now I want to describe like the key tools, like expander decomposition, pruning, and routing, this kind of thing. What exactly it is, and in high level, how come they give the power to get this whole application here. Okay, so that's part 2. And the plan is this. I would like to basically try to answer 2 questions. First, I want to convince you that, okay, first, at least if the graph is the expander or weak expander that I mentioned, then at least you have fast graph algorithm on expander. And then the next thing is that, okay, what if the graph itself is not expander, it's just some arbitrary graph? What do we do? How do people like deal with that? And for each of the question, there will be like the key tools behind it. So we will go through each of them, but let's just start with the first one, which is that when the graph is an expander, then I want to just say that it's algorithmic friendly. Many questions that seems hard become much easier. And here is a first thing is called expander routing. It's a simple task actually to state. So the task here is that suppose you have this weak expander thing, okay, as an input. And the query is the following. So, okay, you have a graph which is an expander. Now I query another graph D. Okay, this graph D, you think of it as like a demand graph. What do I need about this demand graph? First of all, I need that for every node, the degree of node U in the graph D is at most the degree of node U in graph G. And what I want to output is this. Basically, I want to output a set of path, UV path, for all edges UV in D. So think of each edge in D as the demand that you need to connect from, like if there is an edge UV in D, you need to find a path from U to V in the graph G. So this edge UV here, you need to find a path in G. But what we want is that this set of paths should be very nice. So there are 2 things about it. First, each path should be short. And by short, I mean like a subpolynomial or polylog length. And also each edge should appear in not too many paths. Each edge in G appears in too many paths. There are not too many paths that go through it. So it should be short and low congestion. Okay. So like if you don't care about the algorithmic question and just care about the existence of this set of paths, then you can actually show that let's say if the expansion is constant, then these 2 things can be like just locked in. The length and the congestion can be locked in. But now I'm going to relax it a bit to like a subpolynomial factor. And now with this relaxation, it turns out that you have an algorithm that actually just spend linear time. Just spend linear time inside of this graph and return this set of like M path So like note that like there can be m paths in the graph. Like the number of edges in D can be as big as m, right? So you really like return m path in m time. So that's nice. So basically it's like a subpolynomial time per path. And also it turns out that you can also find this path in the distributed model that I mentioned in just like a subpolynomial number of rounds too. So I will not describe how exactly to do this, but at least you should see that, okay, like they are really useful for fast algorithm now. When you have an expander, you can find a lot of short path without congestion in time, which is optimal. And when you think about this in the distributed model or congest model, what does it mean? It means this. When you have this set of path, which is short and like low congestion, it means the following. It means that for any node in the distributed network, right? Any node can basically try to exchange message, which is like degree many message with now any set of node, not just its neighbor. It can just say that, okay, if I want to exchange a message with any set of nodes, I can do it in just into little one rounds if the graph is an expander. And the reason is like, if the node U is near, node V is near, okay, they are not neighbor, but there are like I can find a short path between them anyway. And now I can just send a message from U to V through this short path. And the time to send this message is going to be like this many rounds because the path is short. So this is in contrast to like a normal, like a constraint in congest, when you have that each node can exchange only degree many message with its neighbor. Now you can basically say that you don't need to care about whether node is the neighbor or not. Just any set of nodes you can exchange a message. And basically what it means is that expander allows all-to-all communication similar in congested click, but this will work in now congest. Okay, you need to pay some small overhead instead of just one round. Now you pay into little one round, and but that's good enough for our application. And this is really like the key reason behind how come we are able to reach the result that is on congested click into congest.
So just to make sure, so into the little of one here depends on how good the expand, like whether your expander.
Yes, it depends. Like
so you get polylog if you have the polylog expander.
Yeah. So actually, if the expander is polylog, you're gonna get if you have 5 expander, you're gonna get something like n to little 1 over 5. Yeah. Okay. So another thing I want to show you that things become much easier in expander is the problem of sparsifying the graph. So what is this problem? Suppose that you have an expander, and now you want to compute something called cut sparsifier of a graph, which is just a subgraph of your input graph, right? Such that, first of all, this subgraph should now have just nonlinear in n edges. So normally the graph can have like n squared edges, and note that my definition of expander, I allow the expander to have a lot of edges too, right? It doesn't need to be like a sparse graph. It can have a complete graph in the expander with this definition because I just care about expansion. Okay. So this graph can be dense, can have n square edges. What I want is like a cut sparsifier that have only like near linear in n weighted edges. And it should preserve the cut size. That is, the cut size of every set S in the graph, the cut size in the graph H should be within 1 plus epsilon factor of the whole graph, of the original graph. So yeah, that's what it means by 1 plus epsilon cut sparsifier. And like people like this is a well-studied problem, and there is like a bunch of algorithms to do this. But now I want to just show you that once the graph is an expander, there's like a so simple algorithm to compute this thing. Okay. An algorithm really takes linear time and easily extend to the dynamic setting. But let me now describe the algorithm. The algorithm is simply this. Just go through each edge UV in the graph. Right? Now I would like decide whether I'm gonna include this edge into my sparsifier edge or not. How to decide that? Well, I'm just gonna include it into edge with probability PE. And PE is an extremely simple expression, which is just some number proportion to, like some constant proportion to 1 over minimum between degree of U and degree of V. So that's PE. So you just need to compute the degree of two endpoint, and you know it PE. And now you just sample PH into H with probability PE. And if you say that you're gonna set, like you're gonna pick it, then you set the weight to be 1 over PE, just so that in expectation, the weight is like preserved. So this is the algorithm. Right? So I hope that you see that like, it is like, if you have seen like the way to specify the graph before, PE usually depends on effective resistance, like something that is more complicated. But once the graph is an expander, this PE is just trivial to compute and maintain. If the graph keeps changing, you can just maintain the degree of each node. So that's like, and there are more things that you can do much faster once the graph is an expander, but this is like a key 2 things. Right. The next thing I want to tell you is that not just that expander are algorithmic friendly, they are robust under updates. And this is a key reason why it is so useful in the dynamic setting. Okay. So the intuition that you should have about expander is that it is robust under updates. Because if the graph is not expander, then there can be like this sparse balance cut, right? And such that if you just delete a few edges here, then the graph, like connected component, like a separate, and this is kind of a big change. Now, if instead of the graph in an expander, you know that if you delete a few edges here, you cannot disconnect anything because an expander must have a lot of edges crossing balance cut. And if you want to disconnect something from the graph, maybe you need to delete a bunch of edges here. And if you delete k edges here, at best you can basically disconnect like something like a volume of k out of the graph. Okay. So if you delete few things, the graph can only change by few like volume. The volume that the change in volume is small. So that's the intuition, and indeed it is the case. And what I'm going to describe is this thing called expander pruning that I mentioned before, and it's like the kind of the extreme version of the intuition in the previous slides. So let me describe to you what is like what it guarantees. Okay, so it's an algorithm that, like, suppose I promise you to start with an expander. Now, then there is some edge update. Let's say I delete one edge. So G1 is just a graph at time 1. What the algorithm will do is that it will maintain a set P. P, think of it as a pruning set. Okay. This set P is such that when you look at the complement of P, the complement is an expander. So P is some small set such that everything in complement of it still good. Complement of it is an expander. The next update will come. You might insert something or delete some edge. You maintain a set P, update the set P to P2. The complement remain an expander, and so on. And this set P have the following property. This set P will grow very slowly. If you delete one edge, a set P basically on average grow by just subpolynomial volume. So after I update, after I step, the volume of P is just something like I times into the little one. And the time to update this set is also small. So, question about the statement here. So it means what? It means that basically for each edge update that you will kind of, for each update that might try to destroy your expander, you know that each update can only cause you like a small problem, and you can even identify where the problem is. You identify this set P, and the rest remain an expander. Okay. So, right. So that's expander pruning. And again, like, you know, expander is really necessary here, right? Because if there is some sparse cut like this, if you delete these two edges, then only after two deletion, if you want to guarantee that the complement of P is even connected, not an expander, just not like let alone being an expander. If you want the complement of P to be connected, now P must be this big. Just only after two updates. But here P can manage to grow only slowly because the graph in the expander. Okay. So that's like the two things about why expander is so good for fast algorithm. The first reason is that it's algorithmic friendly. Any problem that you want to solve, you can do it fast in expander. That's why they have application to static and distributed setting. And here is robust under updates. That's why they are useful in the dynamic setting too. Yes.
As for the expander pruning, so you guarantee the subpolynomial update time, right?
Yes.
Yeah, but it's for amortized or each step.
So actually, if you want amortize, it can be just log, like log n over phi, actually, update time.
So you actually guarantee like for each step you have.
Yeah, right. I mean, yeah, so I mean, if you want amortize update time, it can be polylog. Right now, the worst case update time is still subpolynomial factor. So the worst case update time is still not as good as amortize, but I think you can do it. Yeah. Okay. So that's basically why expanders are great. Now, what if the graph in the beginning is not an expander, right? That's the next thing we want to look at. And this is basically expander decomposition, what is for. Okay, so let's see what it is. So an expanded decomposition is the subroutine that when you are given a graph and a parameter phi, it will return a partition of vertices into like a mini parts here. And you know that for each part here, it induces an expander, a phi expander. And at the same time, the number of edges crossing each part is just something like phi m log m. So in some sense, like a graph clustering problem, right? You have a graph, you identify like a well-connected part, and at the same time, not too many edges are like a crossing each part. So this thing always exists for any graph. Given any graph, like basically any graph is really just a disjoint expander plus small fraction of edges. Why this exists? Like one way to see is the following. The slow algorithm to compute this thing is that, okay, you have a graph. If there exists, first of all, if there is no phi sparse cut, then the whole graph is an expander. You just return everything as one component. But if not, then you find a phi sparse cut through it, and then recurse on both sides. Once you stop your recursion, you will get a phi expander. And now you can also show quite easily that the number of edges crossing will be like a phi m log m. Phi here comes from like a fraction of phi sparse cut, and log m here comes from the fact that like when you find a phi sparse cut, you can charge the cut edges to the smaller side, and each node can be on the smaller side at most log m time. That's a high level idea, but yeah, not hard to show this. So, and this is basically the main reason that expanders are useful in any graph, because you can always find a bunch of expander. And now if you can deal with each expander, you just need to deal with each edge, like at the red edges, which is small fraction of the graph separately. You will see like a concrete example how I exploit expanded decomposition very soon. But now if you talk about fast algorithm to compute expanded decomposition, it turns out that you can do it too. And what we show is that you can compute this expanded decomposition, but now I have this relaxation. Instead of just log n, I pay like some subpolynomial factor. But now we can compute it deterministically in like a almost linear time. There is a separate paper that like I show how to do this in the randomized way, and you just pay polylog factor here and there as well. But for deterministic, you still need to pay n to the little one. So now we have seen a bunch of tools. Let's see how to apply the two together to get at least one concrete application. Okay. So what I'm going to do is I'm going to show you how to get a dynamic version of expanded decomposition first, and then use it to get like the dynamic version of cut sparsifier. Okay, so what do I mean by dynamic expanded decomposition? I just mean that you have a graph like before, but now the graph undergoes some sequence of edge updates. And what we want is that we want to maintain this expanded decomposition at every time step. So we want to maintain this partition of nodes. Okay. The number of parts can change now through the steps. And what we want is that for each part, it remains like a kind of good enough expander at all time. And also at all time step, the number of crossing edges are small fraction. It's a small fraction. Okay. This can be done quite easily. I will show you that there's a way to maintain this object with very small update time. Okay. As long as there are not too many updates. Because if there are a lot of updates, you can deal with it somehow, like just reset the whole algorithm somehow. And it's deterministic. So let's see how to get this using our tool so far. Okay. So just recall, right? We have this expander pruning algorithm that if you have an expander and you have an edge update, you can keep growing the pruning set slowly such that the complement in the expander. Now, if you have this expander pruning algorithm, all you need to do is that, okay, given the whole graph, first you compute expanded decomposition to get this first decomposition. Now, when you get a sequence of edge update, okay, so let's like finish this concrete application and we take a break. But okay, so how do you get dynamic expanded decomposition, right? First, just initialize your static expanded decomposition. Now you get a bunch of expanders. Just run expander pruning on each expander. So what will happen when there is a sequence of updates? Well, what will happen is just that you get some prune set on each expander. But note that as long as the number of updates is not too big, this prune set in total is going to be small. So you can just treat, and also like the remaining part, like the complement of the prune set is still an expander. So now what to do with this green thing? They are small because there are not too many updates. So we can just say that, just treat all of this green thing as intercluster edges. So everything inside the red part, think of it as like a singleton cluster. Okay. So the total number of red parts and the original red part is still small. So that's like a kind of easy way to get dynamic expanded decomposition. Okay. And so that's how what we get, like a small update time for as long as the update is not too big. Once the update is huge, you can kind of reset. Not a big problem. Okay.
Very just maybe to see. So like all of these singletons that you're creating now become big enough, so you kind of redo everything.
Yeah, like recompute the whole expanded decomposition and get a new one. but you do this only once in a while. So the amortized update time is small. Okay, now I want to use this dynamic expanded decomposition to get a dynamic algorithm for cut sparsifier. So what do we do? The setting again is that you now, let's say you have arbitrary graph now, not an expander, and this graph undergo updates as well. And at every time, I want to maintain a cut sparsifier of the graph. I want to get cut sparsifier which is defined like before. It has not too many edges, and every cut is preserved. Cut size is preserved. How do we do this? So let's see how to get this thing from dynamic expanded decomposition. The trick is this. We're gonna just kind of repeatedly decompose the graph into expander. So what I'm gonna do is first have a graph called expanded decomposition, right? And now the crossing edges, they are just like let's say they are less than half. There are less than half edges that are crossing. So let this E prime denote a set of intercluster edges, the crossing one. We can now define the graph that is induced by these red edges. Like let's say I just move all the red edges to here. Think of it as a new graph. And what should we do here? We can just call expanded decomposition on this red graph. You will get like now the red cluster with some crossing edges. That is now like 1/4 of the fraction of the edges. You get an even smaller graph and repeat. You can repeat only log n times because at each time, the size of the number of edges on each graph shrink by half. It means what? It means that by repeated expanded decomposition here, you basically you have any graph, you just partition each set of the graph into parts such that each part here partition each set into like a disjoint expander. Not disjoint. Okay, you partition edges into expander such that each vertex can appear in at most log n expander. Because there are log n layers, for each layer, there are really vertex disjoint expander. So that's what we get. And moreover, I claim that you can just maintain this structure dynamically. Because you really just have expanded decomposition on each layer. And it's easy to maintain expanded decomposition. I will skip some details, but it's not hard to maintain this structure dynamically. Okay. Just use dynamic expanded decomposition on each layer. But now it's going to be easy to get dynamic cut sparsifier from this structure. And the algorithm is going to be just this. You have a graph. First, you just get this structure. That is by repeated expanded decomposition here to get into log n layers. For each of this part, for each of the expander inside this structure, you sparsify the expander. But you know that on expander, you can sparsify it so easily just by like a sample each edge here, right? With probability which is proportion to the minimum of the 1/minimum of the degree of the endpoint. And you should be imagined that this information is easy to maintain and you can get dynamic algorithm for this simple algorithm. So for each of the expander, you can maintain sparsifier of this expander, of each of the expander, you can maintain the sparsifier. And what you need to do next is just return your H, the final output, as a union of all sparsified expander. That's a solution. And I conclude that this is a good cut sparsifier. Why this is correct? This is correct because this is where I use some structural property of cut sparsifier. Cut sparsifier are decomposable in the following sense. Like if you have a union of sparsifier, the union of the sparsifier is a sparsifier of the union. So when you union out each of these sparsifier, it's just going to be sparsifier of the original graph. Okay. I will not prove this, but yeah.
So kind of change the epsilon, perhaps, but the
yeah, you kind of like get the max.
right.
Yeah, right. You pay the worst.
Oh, you don't even if they're all the same epsilon, then you still get the same epsilon.
Yes.
Oh,
yes.
okay.
Yeah.
Then it's even better.
Right. So you will pay the error will accumulate if you compute sparsifier of sparsifier, and then you get the sum accumulative of error. But here, you don't. Yeah.
Mm-hmm.
And note that the size of your sparsifier is going to be nonlinear in n as well. Why? Because the total size on each layer, right? Like you spend linear in the size of this expander. So the total size on each layer is going to be linear in n. And now you sum up over all layers, but they are just of n layers. So it's still linear in n. Total size of your returns. And just for the historical note, this actually is the first nonlinear time algorithm for something called spectral sparsifier too. It's like a generalized version of cut sparsifier, and it's the first algorithm. It's like it implies the first Laplacian solver, nonlinear time Laplacian solver. Just kind of want to know it. Okay, so to conclude about this application.
Like the schema term you mentioned, like it's in 2004. It's like the first one
Use this approach. Yeah,
And
it's just decompose into expander and specify each expander. Yeah,
I see. Oh yeah, so this idea, like even like in the first paper, right?
Yeah.
This,
Yeah. Yeah. So we just basically like what I show you is that this first idea actually just works seamlessly in the dynamic setting.
Yeah.
Yeah. So what do we have before we take a break? You see that, okay, by combining expanded decomposition and pruning, you get the dynamic version of the decomposition. And I just kind of show you that, okay, because you can specify expander fast, you get like kind of dynamic version of cut sparsifier. And that kind of like using this idea, we improve the state of the art already. And because there are many kind of other sparsifier, notion of sparsifier in the graph, you get more result using this framework. The fact that you can do fast expander routing, it also implies something else in the dynamic setting. So like, you know, like, yeah, my point is a lot of dynamic algorithm really they benefit from this thing, this framework. And actually this result here, they actually work with vertex expander and even in directed graph. Why do I mention this? Because I just want to point out that this framework kind of is robust enough for many other variants of expander, notion of expanders. Okay. So yeah, before we go to the next approach, maybe we can take a short break for 5 to 10 minutes. Yeah, thanks. Okay, so let's continue. So we saw that dynamic expanded decomposition is useful. Okay, and what I want to show you another thing, which is expanded hierarchy. It's just another way to like deal with arbitrary graph. Okay. So you can think of it as a kind of extension of expanded decomposition actually. Okay, so just recall that we have this thing in expanded decomposition, right? You have a graph, just decompose it into parts such that each part induces an expander, and not too many, like just only 5 fractions of edges across it. Okay. So imagine like a one natural way to get some hierarchical decomposition of a graph from the expanded decomposition. That is, you start with the graph, decompose it. Now, just contract each of the expander into one node. You get a contracted graph G2, and now repeat. Decompose it, get a cluster and contract, and keep doing this until you have like until there is no edges in the graph. Okay, so this will give like by the way, observe that for at every time, right, there are basically something like 5 fractions of edges on each on the cut, and here they're going to be just 5 square fractions of edges. So if you actually set 5 to be like big enough, like small enough, then you can control the number of level instead of log n. You can control it to be like root log n as well. There's something that you can control. But anyway, from this thing you kind of get like a natural tree from this thing, right? So basically, for any node, if they are contracted into like for this node, if they are contracted into this cluster, then you just create an edge between them. So this tree, like this decomposition, give a tree such that everyone here is the original vertices of a graph, and then I can define like the leaf, like V of G are leaf of this tree, and the parent basically correspond to an expander that contain like a parent of node U here. Parent of this guy correspond to like an expander that contains it. There is also a natural way to define the weight of each tree edge as well. That is, it's just the degree, like for each of this node, let's say this node is U, the capacity of this, the weight of this edge is just the degree of the node in G. What should be the weight of this tree edge? Is it just like the degree of this node in G2, which is basically, it's just like the number of cut edges crossing this expander. So that's like just a natural way to define the weight of tree edge. Okay. So that's like very natural tree, but except that this tree is not useful yet, at least to my knowledge. I don't know how to exploit it yet. But it turns out that with just one small tweak to this tree, it's going to be super strong. So let's see what is the tweak. The tweak is to look at a stronger notion of expanded decomposition called boundary linked expanded decomposition. So what it is? So well, it's just the same thing, except that imagine that it's an expanded decomposition that even for each crossing edge here, imagine that you add some more self-load on the endpoint. Let's say beta self-load, where beta is something like it's much larger than 1/5, which is much larger than 1. So you add this self-load for each of the endpoint of the crossing edge. You add beta self-load here. So note that, and I would denote G beta induced by V to be like this graph, the induced subgraph after adding this self-load. And what boundary link expanded decomposition says is that you decompose the graph into parts such that even after adding this self-load, each of this part here with this self-load remain an expander. Okay. So now it might be less clear that this thing exists, but it exists and you can compute it. And note that this is really a stronger notion of expanded decomposition, right? Because if this guy is a phi expander, then without self-load, there must be phi expander, because self-load only increase the volume without increase the cut size. Okay. So why this is useful, at least at the intuition level? So when you have an expander, just a normal expander, you kind of know that all vertices are kind of well connected. Now with this self-load at the boundary, it means that the boundary vertices are like, even after adding self-load, they are still like remain in the expander. So these boundary vertices are even more well linked with each other inside the expander.
We can account for connection.
Mm-hmm. So this is just boundary link expanded decomposition, strictly stronger than expanded decomposition, and you can compute it too. Now with this definition, we can define what we call expander hierarchy. So the tree that I call expander hierarchy is just the same tree that I construct like before, except that for each layer is now defined by boundary linked expanded decomposition instead of just normal expanded decomposition. So I hope the definition is clear. Okay. So, but now with this definition, why is it useful? So it turns out that this tree becomes super strong in the following sense. It actually captures all min cut structure, not just min cut between structure between some pair of nodes. It captures all min cut structure. What do I mean by that? I mean that for every subset A and B, not just pair of nodes, every subset A and B, okay? Pick any subset. You can define min cut that separate A and B from each other. So that's min cut A and B of G. Now you can also define like a min cut of A and B in the tree as well, which is like some set of node on the leaf and some set of node on the leaf here. So it turns out that these two numbers, the min cut of A and B in G and T, they are the same, but up to subpolynomial factor. So the approximation is not great, but this is true for exponentially many cuts. So any graph, you can represent it as a tree that capture all cuts. And moreover, because this hierarchy is just defined based on expander. So I can also show that you can actually maintain this tree in the dynamic setting with small update time. And the idea is just expander are robust and so you can handle updates. But now what is cool about this? Because you have a graph, you can represent it using a tree that preserve basically all cut information. Now, any problem, like tree is like a kind of extreme case of the expander. Like you have expander, things are easy. You have a tree, everything is easy to compute. So dynamic problem on trees is just easy. Actually not dynamic or like any problem on the tree usually it's become much easier. And so from this scheme, right, you can first, if you can maintain, we can show like how to maintain boundary link expander decomposition, which gives you a dynamic version of expander hierarchy. And now all you need to do is just find some dynamic algorithm on top of the tree. And from that, you basically get dynamic approximation algorithm for a bunch of like a stronger problem, like a max flow, min cut, multi-commodity flow, and so on. Yeah. So this is how we obtain like a dynamic algorithm for this harder problem, but with like a big approximation. Okay. So the last thing I want to mention is that it's called Expander-ization, which is quite different from what I have shown you before and not quite well known, but I think it's interesting structurally. So I just want to mention it to you. Okay. Okay, so what is this? It's a way to expanderize lower diameter graph. So imagine that you have a graph with lower diameter, meaning that like every node can reach every node with like a distance d. Okay. So the maximum shortest path is d between any pair of nodes. It turns out that there exists a way, to assign a weight to assign the edge weight or edge capacity. I call it kappa on each edge, such that when you look at this graph with capacity kappa, then it becomes an expander. But at the same time, the total capacity is just increased by a factor of d. So the point, high level point of this is that you can, given like a low diameter graph, you can increase total capacity by a factor of d and obtain an expander. Let me tell you one example. So if the graph in the beginning is just expanded already, it has low diameter, so you actually don't need to increase the capacity at all. So here you don't really need to increase the capacity, but imagine this graph. It's that dumbbell graph, or it's like two, let's say it's a two expander connected by only one edge here. This is far from being expander, right? But what this theorem says is that it's possible to increase the capacity on the part which is like a bottleneck. And you just need to increase the total capacity by something small, let's say polylog factor, because the diameter of this graph is actually small, like log n, right? So you can just increase the total capacity by log factor. And now the part is kind of near the bottleneck. Now it's not a bottleneck anymore, and you obtain an expander. So I think it's kind of interesting structurally, and what I get is like a not a good bound. Like maybe like you don't need like a polylog factor at all. But within polylog factor, this is tight. Because, for example, if the graph is a path, right, then you know that you need to increase the total capacity to be something like n squared. So that the whole graph is an expander. If like the weight here should be like something like n, the weight here should be something like n/2 and so on. So it's tied up to polylog factor. And so interestingly, this thing is useful in dynamic algorithm, but I think it's interesting like as a combinatorial result as well. I wonder how far this would go. Okay. So to summarize, so we have seen a bunch of tools, expander routing, and by the way, there is like a very important open problem that is about shaving interleader 1 to polylog. I think it needs totally different techniques. So that's why it should be very interesting, and it has really a lot of application if you can shave this. We have seen expander pruning, why expander are robust under updates, expander decomposition, and here again, if you can shave the polylog, shave interleader 1 to polylog, it's gonna be great. Like it's gonna imply a lot of things. And we have seen expander hierarchy and this expanderizer of low limit graph. Okay. So now there is like next part, which is to go into details of expander decomposition, but do we want to like go into details, or should we?
It's up to you. The orders may be happy. I think so.
Okay.
I'll be happy.
So let's just spend like go deep just for a bit, and then we. Okay. So I just want to tell you a bit about like how to get expander decomposition deterministically in a linear time, almost linear time. And I wanted to tell you about this because there is something nice called cut matching game that I will introduce during this, and it's good to know about this framework. Okay. So this is just to recall the notion of sparse cut and notion of expander. A phi expander is just a graph without no phi sparse cut. Okay. And what we want is this thing. We know that, okay, if you don't care much about fast algorithm, just keep finding sparse cut and recurse. That's easy. You can do it. But let's see how to do it fast. And one reason that you should see immediately that you cannot get like this algorithm cannot give you near linear time is just because it is possible that when you find a phi sparse cut, you just compute, like you at least need to take linear time and you find some cut. The cut might be really unbalanced, might cut just small part of the graph out, and you recurse on the bigger side. And you might recurse on the bigger side n times. So that's like more than linear time already. So this is like a big bottleneck that you need to overcome. And so on the other hand, if the cut that you find is balanced, right, now at least the recursion depth will be small. So that's a good thing. So that's like the high level idea, how to get fast algorithm. Try to find balanced cut. But we need to say what if we cannot, what if there is no balanced sparse cut at all? What do we do? Right. Okay. So what I will explain is like basically I kind of set phi to be like some fixed parameter such that like let's say there are like m over log n crossing edges, and so phi is something like n over 1 over n to the little 1. And let's see how to do this. So the core subroutine is this thing, which I call balance cut or prune. So let's see what it does, right? It's just a subroutine that given a graph G with parameter phi, it will return you some cut S, where S is on the smaller side of the graph. And one of the two must hold. First, this is just a good case that we kind of saw, we discussed. It's a sparse cut and it's balanced. Like it's like the volume here is less than half, and also kind of almost as big as half. So this is a great case if you have it. Okay. But such a cut might not even exist. So the next case is I call it prune. So in this case is when the case that S can be empty, or if it's not empty, the total volume must be small. But the most important thing about this case is that this small set here must be such that the complement of it is an expander already. So it's like, if you don't find a sparse cut, like if you don't find a balance cut, you said that the bigger side is done. You don't need to look at it again. So now you're good. So either sparse balance cut or small cut, but the complement is done. And now if you have this thing, what I'm gonna show you is like basically how to compute this bow cut prune subroutine in like a nonlinear time, when the quality phi here is something like n to the little 1 over n to the little 1. And I claim that if you have it, then you are done, really. And the reason is just you can keep calling this subroutine recursively and you get expanded decomposition. So for example, you have a graph. If you get a balance cut in the beginning, you just recurse on both sides. Right? So you keep calling bow cut prune subroutine. If you get the prune here, suppose you get a prune case, then on one side you are done. And you only need to recurse on the smaller side. Okay. And at the end, you will like the recursion must stop at some point, because at every time the size of the recursion is half, basically. It's like reduced by constant factor. So the total depth here is log n.
So for the prune case, is it guaranteed like the interpart edges, the number of interpart edges is also small?
So the total volume here is something like 1 over log square fraction. So in particular, the edges incident to this. So the total number of edges incident to the small side is like 1 over log square fraction of the whole graph. So the number of edges crossing this must be like 1 over log square fraction. So this cut itself might not be sparse actually.
Yeah.
But you can charge this cut to the big side, because this big side now is gonna be done.
I see.
Yeah. So just keep calling this thing, and it will give you some vertex partition. And now I claim that you really get expanded decomposition. And the reason is just that, okay, well, whenever you stop your recursion, you stop because of the prune case. And the prune case said that the part that the bigger side is an expander. So each part here is indeed an expander by the prune case. And now I'm gonna claim also that only 1/log fraction of edges will cross the decomposition. And the reason is that so what we can do is like we can charge 1/log, like for every time that we cut, right? We're gonna charge the cut edges now to the bigger side of the cut. Okay. So, and how many times each edge can be on the bigger side of a cut? At most log n time, because you either get balance cut, or if you get a prune case, you even finish. So each edge can stay on the bigger side log n times. And now in the balance case, you get 1/log square sparse cut. So you can charge like a 1/log square to the bigger side. How about the prune case? Okay, this cut itself might not be sparse with respect to the smaller side, but the total volume here is just like a 1/log square fraction of the whole graph. So you can just charge it to the bigger side too.
So overall, you get a log n advantage from this chart.
Yeah.
So it is a 1/log n. Like what's phi like
So this the like every time that I cut it with this sparsity, and here like the fraction is also like you basically charge 1/log square or 1/log square to the bigger side.
Right.
And each time like the bigger side can be on the bigger side at most log n times. So the total number of edges that you cut is just 1/log square times log n. So it's like 1/log fraction of the edges. Make sense? Okay. Good. So in the running time, you'll see that the recursion depth is log n. So it means that all you need to do is like to sum like and the total time per recursion level is going to be nonlinear, because I assume that the bow cut prune takes almost linear time. So the total time for each level is almost linear, and sum them up over log n level, you still get almost linear time. So now all we need to do is like show how to get bow cut prune. Okay. So let's prove this main theorem. And actually we can assume without loss of generality that the graph has constant degree. I will assume this in this part from now. And our strategy is this. We're gonna show that bow cut prune and another process called cut matching game, which is super useful. They are equivalent algorithmically. So each of them reduce to each other. But given that they reduce to each other, this kind of gives you kind of chicken and egg situation. It doesn't help you algorithmically. And the last step is to resolve this chicken and egg situation. But before we go to that, let me talk about cut matching game, what it is. So cut matching game is like a super useful process, even for like a combinatorial reason, okay? Not algorithmic reason. So it's a process for building an expander in the adversarial in the adversarial setting. It's like in the setting where you don't have control over edges that you can add into a graph, you can still construct an expander. So what it is, let me describe it. Imagine that you want to construct an expander, but you start from an empty graph. So it's a graph with nodes V, but no edges. Now, in each round, in round I, what you do, you will choose a bisection of a graph. Put it in like a to AI and BI, right? Two parts have the same number of nodes. You choose a cut. And then some adversary gonna choose a perfect matching, crossing this bisection. And this matching can be adversarial. Can like you have no control. Okay. After that, you add this matching into your graph, and then go to the next round, where now like the next round you can choose the next bisection, and the adversary will add some perfect matching that you have no control again, and this go on. And now your goal, you think of yourself as a cut player. Okay, you choose a cut. Your goal is to choose this cut like smartly, such that only after few rounds, this union of the adversarial matching must be an expander. Okay. So this is like a way to construct an expander when you have no control, like you have only like a loose control on the edges that can be added to it. So it turns out that what we can show that there is a cut player. You can actually choose you can implement a cut player such that you can choose A, the bisection in time which is almost linear, such that after log n rounds, the graph must be an expander. No matter what the matching is, you will get an expander. And this is not this is not new in the following sense, in the sense that okay, if you allow yourself to be randomized, there is an algorithm that is fast, actually near linear, like n log square, something like that, such that this is now like a 1/log expander. If you are randomized, you can do it. If you want to be deterministic and slow, you can do it too. But what we show is that okay, we get a first fast deterministic algorithm for the cut player. But just forget about, even if you forget about algorithm, whether fast or slow, just for the combinatorial reason, this is already interesting. Okay. And the algorithm is going to be actually simple. Our algorithm, what we can do is just, okay, you look at the graph at time I. Okay. Look at the graph X at times I, and call this bound cut prune subroutine. Okay, so it will return you like a balance cut, and what you're gonna do is just choose any set A such that the bisection A contains the whole set S. So if this is the graph at type I, and let's say bound cut prune return you S, then you just return A here, AI here. That's the algorithm. And I will not show you the analysis, but let me tell you the high level idea. Why this is a good thing to do? Because if this is suppose that S here is a balanced sparse cut, right? It means that if you choose the bisection like this, it means that this set after this round will not be sparse cut anymore because there must be an edge crossing this for every node inside S. The matching player have no choice but to add a lot of edges crossing S. So you at least terminate, like eliminate one balance sparse cut. It turns out that after log n rounds, you can actually prove that there is no balance sparse cut at all. And after log n round, the bound cut prune will actually return you like this small set here, such that everything here is already an expander. But in this case, you are good too, because if you choose this set A, now this guy will add, the matching player will add an edge crossing the cut S2. Everything here is already expander, and once you add this matching, the whole graph will be an expander actually. So after log n rounds, you know that you must get a prune case, and just by running this, like proceed on the cut matching game for just one more round, you will be done. That's what's gonna happen. And what I described here is just basically this kind of the same analysis that goes that is used in this paper. Okay. So what do we have here? We have that to implement this cut matching game, you will have log n many rounds. On each round, you just call bound cut prune. So this cut matching game is just the total time to choose this bisection. Okay. So now let me show you reduction on the other way. So there's a notion of embedding. Okay. So when you have two graphs, let's say X and the graph G, and if I embed, like I said that a set of paths P is an embedding of X into G. If P is a set of paths in G, so P is just a set of paths here in G. And for every edge of X, for every edge UV in X, P is like contains a so it's similar setting to the expander routing that we have seen before. And we said that this embedding have congestion-C if each edge is used by a both C path. And if P exists, then we said that X can be embedded into G with congestion-C. Okay. Now, so now that, okay, when suppose that you want to embed a matching into the graph, I claim that you can do this using one single commodity flow computation. Now, like suppose that I give you a set A and B, and I want to embed a matching. Imagine the following. I set the capacity of every edge in the graph G to be C, and then connect the super source S to everyone on A and put the capacity here to be 1. Connect super sink here to everyone in B, set the capacity to be 1 as well. And imagine that I asked about max flow from A to B. Asked about max flow from S to T in this graph. Okay. I denote it by a flow from A to B with congestion-C. Okay. So observe that the following is equivalent. If I can send flow, if the flow here is of size A, right? It means what? It means that I can actually find an embedding of a perfect matching between A and B. And the congestion is going to be C because the congestion of every edge here is C. So if max flow is like of size A, then you have found the perfect matching, the embedding of perfect matching from A to B of congestion C. So the embed, like you get like this perfect matching embedding M. So M embed into G. Okay. So now there is like a kind of a more advanced version of this. Imagine this, like there are two cases. What if your flow here actually is like much smaller than A? Think of this as much smaller than A. If max flow from A to B in this graph is much smaller than A, I claim that it means that you must get balanced sparse cut in this graph. And the intuition is this. It means that when you try to send flow from A to B, then a large part of the flow got stuck, right? You have like, this is much less than A. So a large part of flow got stuck. And it got stuck even when the capacity of this guy is like a log square. If the capacity is even higher, then it means, okay, it got stuck even the capacity of edges here is log square. So you will actually find like a 1 over log square sparse cut. And the fact that a lot of flow got stuck, it means that the sparse cut must be big too. So like it must be quite balanced. Okay. Like this can be proved formally, but at least it should be intuitive. Like at least intuitively, it should be like intuitive to you that if a lot of flow got stuck, okay, it means that like a lot of things got stuck and you have balanced sparse cut. Yeah. Okay.
Max flow min cut.
Yeah, it really follows from max flow min cut. Yeah. And now, but if most of your flow can send through from A to B, it just means that you embed near perfect matching from A to B. You can find near perfect matching from A to B with congestion log square. Okay. So, and we can also say that instead of you can embed near perfect matching M prime from A to B, you can also actually embed a perfect matching M with some fake edges F into G plus F. Right. I'm doing nothing here. I just said that, okay, here I can embed near perfect matching, the green thing, into G. But if I really want to embed a perfect matching, I can just add fake edges here. And I just artificially add the same fake edge here. Then this perfect matching can be embedded into G plus the fake edges. Yeah, why do I doing this? Because in the cut matching game, at least we are talking about perfect matching. Yeah. Okay, so now I'm gonna present you how to implement bulk cut prune using cut matching game. So the idea is just that we're gonna basically implement the cut matching game, right? And there are log n rounds, just like in cut meshing game. This is just from cut meshing game. But now what I'm gonna do is just, I'm gonna specify a meshing player. So far, everything here has nothing to do with the graph G. This is just from a cut meshing game. But I'm gonna specify the meshing player that has something to do with the graph G now. Okay. And the meshing player would just do this. Just do the two cases that I described before. Given this bisection A and B, which is in the graph X, I'm gonna just look at the same bisection in graph G and try to send flow from A to B. If the flow is small, I got stuck quite a lot. You must get balanced sparse cut. And you kind of done. The balanceness is not like a 1/3 yet, but let's say you don't care much about that. You get balanced sparse cut in graph G, and you're done. Otherwise, you get this flow, which is big, meaning that you can embed a perfect meshing with some small fake edges, Fi, into the graph G. And you think of this meshing as the meshing in the for the cut meshing game. This meshing gonna be added into your graph X, this graph X. Okay. So there are two graphs that's going on here: the graph for the cut meshing game and the graph G that you just implement. Like you send arcs like a some arcs about max flow in the graph G here. So once the cut player chooses a cut, you try to send flow. Either you get a balanced sparse cut and you're done, or you get you can embed a perfect meshing into the graph. Look at that perfect meshing and add it into your graph for cut meshing game and proceed to the next round. If at some iteration you get balanced sparse cut, you're done. You just terminate and you are finished with this bow cut prune thing. But if you're not done, it means what? It means that at this point, the graph X is an expander. But you know also that this graph X is an expander that can be embedded into this graph G with some few fake edges. Okay. And the congestion for this embedding is going to be just log square times log n. Because at each round, the meshing have log square congestion, and there are just log n many iterations. So the total congestion is still small. So what it means here? It means that G plus F itself must be an expander, because you have an expander. If you can embed an expander with small congestion into another graph, that graph must be an expander too. So G plus F is an expander. And in this case, actually you can get the prune case. And the reason is that, okay, if F itself actually is empty, then G is an expander, you are really done. Is a prune case where the cut S is like, no, there's no cut. But if F actually, but if F is small, then okay, you think like you have G prime, which is G plus F, and you have like a few edges here, which is F. Okay. If I say that an F here is like a small, if I say now I need to delete F, I can use expander pruning to prune some small thing out, and the rest of this part is a file expander, is an expander. So I just implement the expander pruning in G plus F by you have G prime, which is G plus F, you delete F out, the set F is small. So like it will prune only small things out of it. And the rest is an expander. So I use expander pruning here.
So the you prune a part set of vertices P, like, but the size of P is kind of the same as the size of F here, like
size of P is close to F, but F is small. Because like the fake edges that like in this, the fake edges in each round is gonna be super small. So the total number of fake edges that I add is small. So,
but it's still like if you, so it is linear, right? I don't like. It's linear to it.
So like you should think of F as like something that is much smaller than linear. Like so F is less than n to the 1 minus n to the 1. So and this n to the, like think of F as like a n over log to the 100.
Oh yeah, so the size of P is F times n to the little 1, but that is different from this, right? So that n to the little 1 is different from this n to the little 1. So you get some element. Is that true?
So first, do you agree that F is small?
Yeah.
And when F is small, then when you do expander pruning, P will be proportional to the size of F.
But you don't need an extra n to the little 1.
Like you will need to pay some factor, but
it's smaller than this factor. Yeah, that's fine. Yeah.
Like there will be n to the little 1 here and there, but it will cancel out in a good way.
Yeah. Thanks.
Sorry, so I'm kind of out of time, but let me conclude soon. So with this thing, right? I can basically claim that I get this balance cut or prune algorithm. So let's recap. So we have this graph, the graph G. We want to like get balance cut or prune. What we do is just implement a cut matching game. For each round, the cut matching game set like the cut matching game choose the cut. When you choose a cut, then you try to embed some flow. Like you try to send flow from the two sides. That gives you the embedding of the meshing. If you cannot actually embed a large meshing, like you try to embed like a log-n perfect meshing, and whenever the flow here is small, is too small, you immediately get balance sparse cut and you terminate. Otherwise, you really proceed for log-n rounds and embed log-n perfect meshing with small number of fake edges into the graph. So after log-n edges, log-n rounds, you now embed an expander with small number of fake edges into the graph. And you can conclude that this graph with small number of fake edges is an expander. And from then you can get a prune case by doing expander pruning. That's the idea. And the time to compute like the flow, here is gonna be something like linear, because this is like a special case of flow problem where you can implement it fast using some dynamic shortest path problem algorithm. And the time to choose this cut is the time for like a cut matching game. So the total time here is going to be just something like linear plus the cut matching game time. So that gives like a two-way reduction to each other. Now let me like can I have 5 more minutes?
Oh, good.
Okay. Okay. So now we need to resolve this chicken and egg situation. What do we do, right? What I just showed you before is like, okay, to get balance cut or prune, we need to do cut matching game in this graph of size n. But to implement the cut matching game, you call balance cut or prune in this graph of the same size. So that's not good. Now, the idea to break this like an inter-reduction is this. We're gonna make k-ways partitioning of the graph. And now, what I'm gonna do instead, I partition arbitrarily the graph into k-ways. And what I want to do is that I want to embed an expander of size n over k into each part. So now the time to spend on each of this guy, is a cut matching game on the graph of size n over k. The time to choose the time to choose the cut on each of this graph, you spend cut matching game of size on the graph of size n over k. You need to do it k many instances. Okay. And so that's explain the term here. And now the time to find the embedding for each, when you choose a cut, you need to find the flow embedding that gives you the matching in this one. You need to find the embedding for k parts. But that now correspond to kind of k commodity flow. It's more complicated, but it turns out that it's easy to solve too using some dynamic shortest path algorithm. And the running time is gonna look like kn. So let's not worry too much about this. You can solve it. But once you get this kind of recursive structure that reduce the number of nodes by a factor of k, then you are good. Except that, suppose that you are kind of done and you suppose that you have embedded an expander xi into each part bi. If you successfully embed an expander into each part, you are not quite done yet. You need to embed just one more expander. That is kind of an expander between parts. But this is super easy. It's like a graph of size k now, which is super small. Not worry too much about this. But if you do this, it's gonna work. And the recursion.
You were thinking of k as a constant.
I think of k as k is gonna look like this, something like a subpolynomial factor. And the way I think, and with this kind of reduction, you get that to solve bound cut prune, you spend nk time plus k times this thing. The cut matching game reduced to bound cut prune as well by calling bound cut prune log n times. So now you reduce bound cut prune to this plus k times log n and this thing. You can solve this recursion. It's gonna look like kn and log to this thing. And if you set k to be nice enough, then you get into a almost linear time. Okay, just to conclude, that's how we get fast and deterministic expanded decomposition. And the key is to get bound cut prune algorithm that is fast. And the idea is just to see that they are equivalent, two processes are algorithmically equivalent. Bound cut prune and the nice thing called cut matching game. And we break this chicken and egg situation by basically recurse on the instant of smaller size by a factor of k. To implement this recursive structure, like where you break it into k parts. You need to like do some k completely slow algorithm, but you can do it. Yeah. So that's the key idea. Okay. So now, yeah, this will be finished soon, super soon now. Yeah, this is like last part. Yeah. So now, what we have so far, right? You have seen a bunch of tools related to Expander and how they are useful for fast algorithm. And I think that is like a very promising way to go from now. That is, try to generalize the notion of Expander and the tools that we have seen to a more general setting and solve more problems. Let me give you just one concrete example. You can define a directed expander, for example. A natural way to define expander in directed graph is just a graph such that you call it directed phi expander. If for any cut, it's the same thing like before, except that you have large cut in both directions. Both in edges and out edges are big relatively to the volume. So that's just one way to define a directed expander. So yeah. And once you define like this, right? Now you can ask about directed expander decomposition and so on.
Your degree is also both ways.
The degree is both ways. Yeah. And so there is a natural way to get directed expander decomposition. And what it is, you just imagine the process where you have a graph. And once there is a sparse cut, like meaning that there is a cut such that at least in one direction, there are few edges. Then you cut and repeat and recurse on both sides. If you keep doing this, you will get the following object where it can be defined like this. You have a graph and a parameter phi. And now the output is just like some set of edges E prime. Think of the E prime as a edges that you cut. Okay. It's like edges along the sparse cut. This E prime is going to be small, phi fraction of things. And what do we get after that? You get that if you look at the strongly connected component in the graph after deleting the E prime, the red edges, each of the strongly connected component would not just be connected, but they are phi expander. So I mean, like the picture looks like this, where you basically have strongly connected, which are expander, a phi expander, and the red edges are like phi fraction, and you have a DAG of expander after deleting phi fraction of edges.
The black edges between the things could still be negative.
The black edges can be huge. Yeah. So, or if you start with the DAG, for example, this thing might not do anything. Like it will just give you like the whole thing is every singleton is like a cluster on its own. But if the graph is not a DAG, then it gives you some interesting thing.
Are there any applications?
There is, yeah. So, by the way, just want to contrast before going to application. You can see that for normal expanded decomposition, right? It's just almost the same thing, except that you just say that, okay, after removing phi fraction of edges, you get disjoint phi expander. In the directed case, you remove phi fraction and you get a DAG of expander. So applications so far are not too many, but there are. So what I do is that I use this directed expander decomposition to get a faster dynamic algorithm for reachability. reachability, which is just connectivity in the directed graph, is useful somehow. To do that, we need to do directed expanded pruning as well. So this just like can be transferred to the directed case. Okay. By the way, I just want to mention another one, which is like a recent breakthrough in algorithm community, which is just a problem of negative weight shortest path. People know how to compute shortest path in the graph with negative weight using Bell-Manford algorithm from 60 years ago, I think. That takes quadratic time. And just last year, Bernstein, Nanopon, Nanomkai, and Wolf-Nelson showed the first nonlinear time algorithm. The key object in this algorithm is called directed low diameter decomposition, which is just so closely related to directed expanded decomposition that I just showed. Happy to talk more about this. There should be more application for this directed expanded decomposition thing, even in combinatorics. I hope, like for example, to find some nice structure in the directed graph using this thing might be useful. And the concrete open problem, which is expanded routing and expanded decomposition, both of them just sharing this interleader one to polylog will have like a wide range application. So I just repeat it again. And having a super simple algorithm for expanded decomposition would make this whole talk practical. Right now, it's not quite practical, I guess. Yeah, that's it. Yeah, thanks.
More questions? Do you lose the polylog in the chicken egg part of the expanded decomposition? In terms of the range.
So you mean
what are the bottlenecks to get the polylog?
Okay. So the bottleneck to like that I don't get polylog is that when I try to do this thing, to do this k-way recursion here, this structure of recursion, like you need to set k to be big enough, so that like, I mean, how to say this?
Balance the two term.
To balance the two term, yeah. And once you use this kind of recursion, you get something which is not polylog.
You need a better reduction.
We need a better reduction, yeah.
Or a different method, of course.
Yeah. I mean, and interestingly, like so many, like in the recent years, like last, let's say 5 years, right? Many fast algorithms really have this kind of recursion structure. Yeah. And that's the reason why there are like so many papers that give you interleader one factor. And like it's always like when people get polylog instead of interleader one, it's always much smarter than this one. So
the negative weight shortest pass by Dangkong, like that one is near linear. Right?
Yeah.
So it's great. Like,
it's very smart. Yeah.
Yeah.
Right.
So is there some way of kind of getting this recursion directly without going through the cut matching? Cut out the second line.
Yeah, I am not sure.
How recursively directly try to do that.
Yeah.
I mean, you can probably translate what you're doing in some secret.
I understand.
But I'm asking kind of.
Just make it simpler, like argument. Yeah. I don't know. Yeah.
That's one.
All right, then thanks a lot.